So Hess's law is a chemical law which allows us to gain an appreciation about how the sums of different reactions that we use can be added up to equal some n total reaction. So there's a couple practice problems right here that I took off the internet. And then one problem that we worked on in lab the other day that was a little bit tricky for us to work our way through. And I'll go through the steps with you on solving Hess's law problems. So what happens in Hess's law is we're generally given some sort of enthalpy for reaction. And actually, as I'm looking at these reactions right here, these aren't H's, these are delta H's. I think there was something that got crossed up in translation as we went over. And we want to look at the overall delta H for the reaction that's taking place. And so when we look at this reaction, we can see that we're trying to say that water reacts with carbon to produce carbon monoxide and hydrogen gas. And so we need to come up with a way of adding these two steps here to come up with that end result. So the easiest way to do that is to look at our end reaction and figure out what we need to do to the other reactions to make it happen. So for example, we can see that we want water to be a reactant. When we look at the second reaction here, this reaction 2, we can see that water is written as a product. So what we want to do is we want to try to rewrite that reaction with water as a reactant. So what we're left with is 2H2O decomposes into 2H2 plus an O2. Okay, so we've taken care of that step, which is good. Now remember, when we do that, we change the enthalpy because if we flip a reaction, we change the sign. So the enthalpy for this reaction now becomes positive 483.6. It was negative 483.6 before. So that takes care of the products right there. We also notice that there's no coefficient in front of this water right here. And so that means we only want 1 mole of water. So if we only want 1 mole of water, what we want to do is we want to multiply this entire reaction by 1/2. And if we multiply the reaction by 1/2, we also want to multiply the enthalpy for reaction by 1/2. And what we end up with now is a situation where we're left with 1 H2O yielding 1 H2 plus 1/2 of a mole of O2. And now our enthalpy for the reaction becomes half of 483.6, which we can come over to our calculator here and say 483.6 divided by 2 is going to equal 241.8. Okay, so now we can say that our enthalpy, our delta H, equals 241.8, and it should be kilojoules. Shame on me for not having that up here. Kilojoules. So we're partway there. Okay. Now what we want to do is we want to look at that first reaction. We can see a couple things. First thing we can see is that we want carbon as a reactant. Carbon is already written as a reactant, which is good. Carbon monoxide is a product. We want it to be a product in our end reaction, so that's good. So now the only problem is we have 2 moles of carbon and 1 mole of carbon, what we're looking for right here. So all we're going to do is we're going to cut this reaction in half. Okay, and so what we're left with here is we've got our 2 C's plus O2 yields 2 CO with a delta H equal to negative 221.0 kilojoules. But we want to divide that in half because we only want 1 carbon monoxide. So we divide it by half, divide it in half. And what we end up with is, go ahead and move this reaction down a little bit. Oops. Give us a little bit more space. And when we do that, what we can see that we're left with is C plus O2. Actually cutting it in half, it'd be 1/2 of an O2 yields CO, with our delta H now being half of 221.0, which would be 110.5 kilojoules. The sign being negative because it was negative up here. We didn't flip that reaction. So now when we add these two reactions together, we can see we end up with C plus 1/2 O2 plus H2O yields CO plus H2 plus 1/2 O2. Well, that looks like a mess, except for the fact that we can recognize that the half O2 on this side and the half O2 on this side are like terms, so they're going to cancel, and so they go away in this reaction. And now what we're left with is C plus H2O yields CO plus H2, C plus H2O, CO plus H2. So we're in good shape. So now what we need to do, because we've just added those reactions, is we have to add our enthalpies. So if we come back over to the calculator, we can see negative 110.5 kilojoules plus 241.8 kilojoules equals, let me try that again. I did something funny right there. We end up with, oh, I know why I did that. I was assuming the negative was a minus sign. Negative 110.5 kilojoules plus 241.8 kilojoules, and we see we get a sum total of 231.3 kilojoules. Delta H is equal to 231.3 kilojoules. The positive sign for this tells us that we need to add heat in order to make this happen. And so therefore work must be done to the system in order to make this happen. And so it makes sense that, that this is going to require energy to take place. So we can take a look at another example here. Standard enthalpy changes for the formation of aluminum oxide and iron 3 oxide are those steps, and we're trying to find the delta H for iron oxide plus 2 aluminum gives us Al2O3 plus 2 Fe. The nice thing about this is by inspection, we can see that we want 1 iron oxide, we've got 1 iron oxide. We want 2 aluminum, we've got 2 aluminum. We want 1 aluminum oxide, we've got 1. We want 2 iron, we've got 2 iron. So we're not going to have to change the multiples for these things. Now all we need to do is to add the 2 steps of the reaction so that our reactants are showing up as reactants and our products are as products. So we can see that we want Fe2O3, iron 3 oxide, to be a reactant. It's written as a product under the formation enthalpy. So we want to reverse that second reaction. You can see aluminum is a reactant. We've got aluminum as a reactant in the first reaction already, so we're just going to leave that one alone. So what we're going to be left with is 2 aluminums plus 3/2 of an O2, because that what was given to us, gives us Al2O3, with a delta H equal to negative 1,675.7 kilojoules. Now the second reaction we said we want to flip, so we're going to write it as Fe2O3 breaks down into 2 Fe's plus 3/2 of an O2. But because we flipped that reaction, we're going to flip that sign. We get delta H being equal to positive now, positive 824.2 kilojoules. When we add these 2 reactions up now, we can see, we can do this by inspection now, okay? We can see that the 3/2 O2 are going to cancel out, which is nice, and what we're going to be left with is going to be 2Al plus Fe2O3 yields Al2O3 plus 2Fe. Come up here, and we can see that that's the form, Fe2O3 plus 2Al. These are written reverse, but that doesn't matter. Yields Al2O3 plus 2Fe. So now we just have to add up our enthalpies. And so what we're going to do is we're going to come over here, and we're going to say negative 1675.7 kilojoules plus 824.2 kilojoules equals negative 851.5 kilojoules. So we come back over here and we can see delta H is equal to negative 851.5 kilojoules. Okay, one last reaction. This one was the doozy from class the other night. It's a little messy looking here because when I copied and pasted it over, it did it as an object, and because it blew the size of the object up, it looks kind of ugly. What we're left with here is a tricky situation. Now, if you stick to the idea of trying to make your end result reactions look like your beginning parts, it becomes a lot easier. I think some of the trick that some of you guys were having the other night is you were trying to reduce it and make it look exactly the same. Well, one of the students in class suggested that you can get to your end result and then divide your end result by some factor in order to get your final answer. And that's what we're going to do in this situation here. It happens to be a little bit easier. So we want to have the lens that we want FeO as a reactant. Okay, so when we look at our 3 reactions here, reaction 1, 2, and 3, we can see that FeO is a product of reaction 3. So the easiest way to work on this is to understand that we want to make sure that we cancel or that we have our FeO as a reactant. So we're going to flip reaction 3. Okay, we're going to flip reaction 3 first. So reaction 3, you have to bear with me because this is going to be written in a variety of steps. So reaction 3 we're going to flip to say 3 FeO plus CO2 yields Fe3O4 plus CO. Okay, and because we flipped this, our delta H now is going to change to, sorry about that, our delta H is going to equal negative 19.0 kilojoules. So we flipped that thing around. All right, so that took care of that part. So we have our FeO as a reactant. Okay, now I wouldn't look at the COs and I wouldn't look at the CO2s because they show up in all three reactions here and all three reactions here. It's kind of like when we balance reactions. If we had something that showed up in a variety of spots, we didn't worry about it. We assumed that they were going to take care of themselves. So I'm going to bring my attention next to the Fe solid. Okay, we can see that we want Fe solid as a product of reaction. So that's good because we've got Fe solid already written as a product of a reaction. So we're going to go ahead and rewrite reaction number 2 just that way, where we've got Fe2O3 plus 3 COs yield 2Fe plus 3 CO2s. So what we've taken care of so far is we've got our FeO and our Fe. So we've got that all taken care of. The problem now is we've got Fe2O3 as a reactant here, and we don't want that in our final reaction. We've got Fe3O4 as a product. We don't want that as a final reaction. But if we look at reaction 1 right here, okay, if we look at reaction 1, what we can see is if we flip that reaction, we can start setting it up so that your substances will cancel. Okay, so we're going to take reaction 1 and we're going to write it flipped. We're going to write it as 2 Fe3O4 plus CO2 yields 3 Fe2O3 plus CO. And because we flipped it, we're going to rewrite this so the sign is going to say positive 47.0 kilojoules. We didn't touch that second one because we didn't flip it or anything. We left it the way that it was. Now we've got some things to look at down here. Okay, and the things that we have to look at here are that we've got 2 Fe3O4s up here, and we've only got 1 down here. So we know we want to try to make that cancel. Again, we're focusing our attention on everything except for the CO2s and the COs because those belong to everything. So if we know that we want that to cancel, all right, what we can do is we can say, all right, well, let's take that third reaction, the whole thing, and multiply it by a factor of 2. And if we multiply that by a factor of 2, we get 6 FeO plus 2 CO2 yields 2 Fe3O4 plus 2 CO. So we can see when we add these up, okay, your Fe3O4 will cancel with this Fe3O4. So just for the sake of keeping things straightened out, I'm going to cross this out. We'll leave it here, but I'm going to cross it out because we've rewritten this reaction here, okay? So that took care of our Fe3O4s. Now the other problem is we've got these Fe2O3s that we want to cancel. We've got 3 in the first reaction. Oh, before we do that, we need to remember that because we doubled that bottom, we want to double our enthalpy. So now we're going to be left with a negative 38.0 kilojoules. Sorry, taking one thing too fast at a time. So we'll cross that out. Okay, so we're making our changes here as we go. At first reaction, we can see we have 3 Fe2O3s and there's only 1 down here. So what are we going to want to do with the second reaction? Let's triple it. Okay, triple it. So if we triple it, what we're going to be left with is, first I'm going to give ourselves a little bit more space so that we can go ahead and triple that without a problem. So we're going to triple it to say 3 Fe2O3 plus, 9 CO yields 6 Fe plus 3 times 3 is 9 CO2. Sorry about that. I'm looking at a lot of things here at once. Okay, we can get rid of this here. All right, so now it looks like we have an utter mess going on. Okay, but trust me when I say we don't. Okay, because when we look at this now, okay, what we can see is that we've got a bunch of things that are going to cancel out. So we'll cancel this out here to keep this straight. Okay, we tripled it, so we want to triple the negative 25 kilojoules, which is now going to be equal to negative 75.0 kilojoules. And we've left reaction 1 alone all along, so we might as well leave it as positive 47.0 kilojoules. Okay? Looks like a mess, but trust me when I say that it's not, okay? Because we can see when we look at this reaction, all right, the two Fe3O4s will cancel down here, okay? So those are gone. 3 Fe2O3 cancel with these right here. All right, now probably the easiest thing to do would be to add up everything that you've got left and see what we've got. Okay, so if we add it all up, I'll put it in blue this time so we can see what kind of new stuff is going on here. What we're left with is CO2 plus 9CO plus 6FeO plus 2CO2. That was all the stuff on the reactant side. CO, 9CO, 6FeO, and 2CO2 yields CO plus 6Fe plus 9CO2 plus 2CO. Well, we've got some terms that we can combine together, okay? So what we can see here is 2CO2, and CO2 here is 3CO2, okay? Plus 9CO plus 6FeO yields, and then we go on this side, we can see 3 COs on this side, 3CO plus 6Fe plus 9CO2 on this side, okay? Make this page a little bit bigger. All right, so now what? Okay, still looks like we have a little bit of a mess going on. Well, not really, because now we can see that we've got 9CO on this side and 3CO on this side. These are all going to cancel away. All of these are going to cancel away, and this is going to change to 6CO. Okay, now what? Well, same thing on this side. We've got 3CO2 here and 9 here, so all of these would go away, and this is going to change to 6CO2. Well, the FeO is not going to do anything, so we're going to be left with 6FeO, and we're going to be left with 6Fe. Oh, great. Now what? Well, it's really actually nice and easy, because what we can see is we've got a common set of terms right here. All right? Because when we go back to our original reaction, we wanted 1 mole equivalents of everything. Down here, we've got 6 mole equivalents of everything. So what we've done is we've added everything up right now. So if we go ahead and we add up the total kilojoules here, okay, that'll give us the total kilojoules for 6 moles of reaction. So what we're left with is 47 plus negative 75. Oh, I almost did it again. Let's come back here. 47 plus negative 75 plus negative 38 equals negative 66. I did something wrong here. I know I did something wrong here. No, I didn't. Okay? Equals negative 66. Okay? So what we end up with here is we get a sum total of negative 66 kilojoules. All right? So now we come down here, we can see our delta H equals negative 66 kilojoules. So we're done, right? Well, not quite. Almost. Not quite, though, because we know that we only wanted 1 mole equivalents. So how are we going to take this and turn into 1 mole equivalents? And this is going to, how is this going to be affected? Well, we're going to divide this whole thing or multiply this whole thing by 1/6. So that's going to be CO plus FeO yields Fe plus CO2. But if we multiply that by 1/6, we also have to multiply this by 1/6. And what do we get? Delta H is equal to negative 11 kilojoules, which is the answer you guys came up with. So that's how you work your way through Hess's Law problems. Like I said, this last one was a bear, but it's very straightforward. The one thing I want to remind you not to forget is that the stoichiometry stays the same. So if you were asked how many kilojoules of heat would be produced for 2 moles of FeO, remember, 1 mole of FeO for 11 kilojoules, so you can use that as a mole ratio and figure your stoichiometry out from there. Okay, so best of luck, and I hope this was able to work out well for you.